Today we are going to see the theory related with cantilever. Now, what is a cantilever? A cantilever is a beam fixed horizontally at one end and loaded at the other end, provided the weight of the cantilever must be negligible. So, as shown in figure, we see that AB represents a beam which is fixed at one end A and the end B is free, where we can apply the load mg so that the bending of the beam will take place. When there is a no load applied at the end B, then the beam will remain horizontal. So such a beam is called as unloaded beam. But when the end B is loaded with mass m, weight mg will act on this end and the beam gets bended in the downward direction. Such a beam is called as loaded beam, and the distance through which the beam is displaced or bended is known as the depression. It is denoted by y. Now let us consider, or let us obtain an expression for depression of cantilever. Now, as shown in this figure, AB is a beam and end A of the beam is fixed and end B is free, where we can apply the load. So now this is nothing but a cantilever AB. Now consider a point P which is situated at a distance x from the fixed end, and therefore the distance of point P from the free end will be L minus x, where L represents the length of the beam or cantilever. Now when we apply a load mg in the downward direction, then its equal reaction will be at point A in the upward direction. So these two forces are separated through distance L. Therefore, if we try to find out the bending moment about point P, then we write bending moment about point P is equal to mg L minus x. But bending moment is also given by yiz upon r, or that is y ak square by r, where iz is called as the geometrical moment of inertia of the bar. Now for equilibrium, we must have this bending moment within the material yiz by r must be equal to the external couple, that is, or bending moment due to external couple, that is mg L minus x. Therefore we write 1 upon r is equal to mg upon yiz L minus x. Now consider another point Q, which is at a distance x plus dx, or the distance PQ is nothing but dx. If r is the radius of curvature of this concave surface of the bended beam, then we write dx is equal to r into d theta. Therefore r is equal to dx by d theta, that is 1 upon r is equal to d theta by dx. Substitute this value in equation 1, we get d theta by dx is equal to mg upon yiz L minus x, or d theta is equal to mg upon yiz L minus x dx. Now we draw tangent at P. So the tangent at P intersects the vertical line at C, and another tangent drawn to Q intersects the vertical line at D. Therefore, the distance CD represents the depression dy when we go from point P to point Q. Now from this diagram we find that dy is equal to L minus x into d theta, or d theta is equal to dy upon L minus x, or dy upon L minus x is equal to mg upon yiz L minus x dx using equation 2. Therefore dy is equal to mg upon yiz L minus x bracket square dx. Now we find what is the total depression of the beam if we consider point P at A and point Q at B. Therefore, the total depression, that is nothing but dP dash. So, y is equal to integral dy over length 0 to L. So, substitute the value 0 to L, that is mg upon yiz L minus x square dx. Therefore, y is equal to mg upon yiz 0 to L. We expand this term L minus x square, that is L square minus 2Lx plus x square dx. Now find out the integral of each term. So we get y is equal to mg upon yiz L square into x minus 2L x square by 2 plus x cube by 3 over the limit 0 to L. So we get y is equal to mg by yiz L cube. Here we get L cube and L square by 3. So this get cancelled, we get only L3 by 3. Or finally we get the depression of the beam y is equal to mg upon 3yiz into L cube, or mg upon 3y ak square into L cube. So this is the expression for depression y of a cantilever when it is loaded with mass m.